Okay, everybody, welcome back. We're at a fascinating first session on space weather from NASA's perspective and Dr. Lika Guhathakurta. And now we're going to move into the operational part of space weather and how that impacts us here on Earth. And those of you that are watching online and here in the room, oh, gee, if you use anything like maybe smartphones or tablets, or maybe you drive with GPS systems, you might want to pay close attention to this. So as is customary, we're going to roll an introductory video just to give you an introduction to Bob Rutledge and the Space Weather Prediction Center, and then Bob will kick off his talk. And please, if you're online, you have any questions, submit them on through the Facebook page. We'd be happy to ask them once we receive them. So here we go. Take a look at the introductory video.
Space weather affects technologies. As conditions develop, we put out alerts, warnings, and watches to our customers so they can take action.
There's different types of impacts on communication systems. And the HF, we call the high frequency, which is that band of communications, 3 to 30 megahertz. But it's a very important band of radio communication because it's used widespread. It's used, for example, by the airlines.
HF radio is most commonly used for position reporting when you're going across the ocean airspace, which is devoid of radar. And ATC can't see you, so it's up to you to report your position and your altitude and your speed.
HF works great most of the time, except during a big flare. And during a big flare, that HF communication capability could be gone within a minute or two. So as soon as we see something happening in there, or we see a flare, it's one of the first things we do is alert the aviation community, hey, big flare, HF's going to be impacted.
Once we know that there's an event going on, then the aviation industry and the airlines can react to that. They can alter their routes over the poles. They can lower the altitudes that they're flying at, or maybe decide not to fly at all in the interest of their passenger safety.
So that's just one example of how the HF is used, but the emergency response community will use it a lot too. It's one of their primary backups.
When you've lost connectivity between certain government agencies, it gives you that long-range coverage to talk from out-of-state to federal governments or from the FEMA locations to the state emergency operations centers.
So if we've got a big hurricane impact in the coastline, whatever big city, we've got the cell towers down and whatnot, we've got emergency communication folks in there. Those folks are very familiar with space weather and how it impacts their systems.
Here in recent years, it was used during Katrina when we had a lot of communications outages down there. It was also used during Hurricane Ike. There was an outage of the telephone circuits with the Texas State Emergency Office, so it was used in both of those situations.
So when we talk about backup, especially for the airlines, typically they'll have SATCOM, so that'll be satellite communication.
The satellite technology that emergency responders use could be GPSs, could be satellite phones, satellite data terminals.
Space weather events can impact SATCOMs. The impact can range from a nuisance to loss of a spacecraft. So we will give them the heads up. If we have space weather events, flares, whatnot, they need to know what's impacting their systems. Situational awareness is key. Time is of essence to these folks. Again, it's life and death.
Okay, we're on the Thomas Fire.
All right, thanks very much. Thank you, Dave, and thank you to the sponsors and organizers. Pleasure to be here. I also want to thank Lika, a longtime friend and colleague of mine. She did all the hard work for me, so I think we should do this often in that order, so you get to go first. So there will be some repeats in here, but I'm going to give you my perspective on the operational end, my perspective on dealing with the users and the impacts. So you'll see some repetition, hopefully not too much. If it's too much, quick chance to check email, maybe set a new high score on Candy Crush. I don't know. If you get that emergency phone call, go make a snow check. I understand too, but I'll try not to be too repetitive. And please stop me anytime for questions. So I will run back through a little bit on the sun and the solar cycle. You've seen some of this. I'll give you my take, and really my take. I focus a lot on the high impact, low frequency perspective. As Lika said, there's space weather going on all the time. That's certainly true. And I'll make some points about, when is space weather truly significant? And from my perspective, I mean, when does it really present a risk to critical infrastructure, for example, or when is it a big impact to aviation operations? So that's kind of how I approach this. The sun is amazing, it's cool, it's magnificent. There are huge flares, but I find myself having to temper the message sometimes because I deal with a lot of the FEMA, DHS, critical infrastructure sectors. So I want to make sure when I say it's massive or huge, that it really means that from an impact perspective. And so maybe a little bit different tone for me on that. I'll walk through a typical sequence of events. I think I almost want to apologize to everyone else in this room for using the term weather, because I think it implies a predictability that I can't live up to right now in the state of science, but I'll elaborate more on that. And I'll walk through the major phenomena, how we describe those, and I'll talk about the impacts to each of those. I'll also make some statements about what we're doing to improve this in the products and services, where we are. People compare us sometimes to weather modeling, 40 or 50 years ago. I think that's pretty fair in general. And I think we will continue to improve, but we may never truly converge with weather modeling in the skill and predictability that we have today with multi-day predictability with some skill. As you'll see as I talk about this is a very eruptive phenomena that are driven, all of a sudden the system is running along and it gets a big impulse, a big disruption, so we can't always predict those very well. So sometimes just by the nature of the phenomena, how the eruptions play out with the sun, how those shocks really reset the Earth system. Sometimes we'll go as far as we can on providing value-added services, but there will be limitations in the long run. Yep.
Let me turn your microphone off. Can you hold this one? Do you mind? We're getting a little echo on the stream.
No one wants that. Okay. Thank you. Is that better? Okay. If not, let me know. And then I think this issue has gotten a lot of attention, and primarily from the risk to critical infrastructure, as I said, and really the power grid. So when you talk about losing the bulk power system, really the supply in the system, the cascading effects to that are really pretty catastrophic. So this issue is getting a lot of attention, and there's progress being made on that, and I'll talk about that as well. And as you know, much like weather, the key of the business is observation, so I'll make some comments there too. So Lika covered this already, so I'll give you the easy version of this. And from my perspective, keeping all of this straight, and I'll talk about it again as I walk through the phenomena, is to understand time scales, where the impacts are felt, and how does this play out? So if I say a solar flare, for example, so that's really the first observable in the sequence of events. That's a flash of light. So no matter where it happens on the side of the sun that we can see from Earth, it's going to affect Earth. It'd be like me holding a candle and walking around this room. It doesn't matter exactly where you're looking at me from. You can see that light source the same. So that affects the day side of the Earth. That's light and radio waves, so it pays no attention to the magnetic field lines shown on the right side of that graphic that represent the magnetic fields of the sun. So when we talk solar flares, they're a day side effect. When we talk charged particles, and I'll do a little steering with my one free hand with the cursor here. We talk charged particles, we're talking about tiny, tiny bits of matter, protons, electrons, most of the stuff that most people have forgotten from school. And those are really small, going very, very high velocity, so they have the energy to pass through astronauts, satellites, and space. But the important part about them being charged particles is that they have to do work to get across these magnetic field lines. So when I talk about the impacts from a radiation storm, you'll see those focused in patches at the poles, and you already saw it show up in what Lika said. But the radiation part is geographically toward the pole because of that reason. And then the last piece, the one we talked about, the coronal mass ejection, I'm glad not to have to introduce that term. For the first time, I'll say CME from here on out. So as Lika said, billion-ton cloud of superheated gas or plasma moving at anywhere from 1 to in excess of 5 million miles an hour. And the most important part from understanding how this works is to understand that this has a magnet built into this plasma. So whatever magnetic field it had at the sun, essentially it will transport that, and then it will interact with and disturb, in some great movies earlier, of how that will disturb the Earth system and how it will drive a geomagnetic storm. So we'll talk about that as well. So this is the sun today. Essentially, I pulled this last week. It's not much different today, but we really have no big significant sunspots at this time. So this is a really easy day for me to make a forecast. I can say from a big picture perspective, no significant activity is going to occur today, and I will most certainly be right. However, this is what the sun looked like in October of 2003, what I would argue is the last truly significant series of space weather storms, and I'll show you why I make that point. But you can see it's a much different sun than we have today. It didn't change colors, different spacecraft obviously, but these are big, big, complex sunspot groups, and this one was in view when it rotates left to right and then takes about a 2-week trip across the face of the sun. So when we get one of these big active regions, we can see elevated periods of activity for 10 days, a week, something on that order. But this was producing lots of eruptions and came into view. What's really difficult, though, is to say exactly what's going to happen and when, and I'll show you a couple examples of that. Introducing a completely new concept here, and if we locked the doors, for example, and I asked all of you very bright weather people to give me a hurricane season forecast for next year, I'm sure you would all unanimously agree. We'd put out the chart, everything would be fine. No? Right, that's right. So you can see we took the world's greatest solar physicists, the modelers of the sun, and they make predictions of what the next solar cycle is going to be. And the last time we did this, we waited anxiously for a couple of days. I think as my colleague Bill Murtaugh tells it was waiting for the white smoke or the black smoke, almost as if they had elected a pope, and this was the result of that prediction. So it's either going to be very small or it's going to be very large, which is really, it's not that these people aren't as good as anyone in the business. It just really is really hard to say what's going to happen over the next decade. So no disrespect at all to those individuals. It's just something that's a little bit beyond us. Now, most certainly, so that's a decade ago when that prediction was made. That's not to say that models of the sun haven't come a long ways in that decade, so we'll see what these new sunspot predictions happen. But I can tell you I see violent disagreement within the community still about whether next solar cycle 25, is going to be elevated again or be quite suppressed. So we just don't know. So I've told you what it is, and so has Lika, and then I will make the point here in a bit of why that's not, from a high impact, low frequency perspective, why you can forget essentially that a solar cycle exists. So this is how, in fact, it played out. You saw this earlier. So in reality, it was beneath that bottom line. So this is roughly a number of the spots and groups of the sunspots. Trends reasonably well with some forms of activity. So that prediction was between 75 and 100. And in reality, in April of 2014, we were just over that 75 number. So it was lower than expected, and it was also, the peak was shifted by about 18 months. These guys did me a great favor, and if this business ever doesn't work out for me, I'm going to write a greatest hits book on all the emails I've gotten. But the original peak of solar max was predicted at the end of the Mayan calendar in December of 2012, so that generated a lot of very interesting emails. I'm sure you guys have seen some of those as well. So this goes back to really making a point that the big storms can happen in lower than average solar cycles. So we don't need a big cycle to have the biggest storms. You don't need the biggest hurricane season on record to get the one Cat 5 that makes landfall in Miami. It's the same in the space weather business. And these are two examples. So the 1921 storm was pretty fantastic. And the 1859 storm, which was already mentioned, is fantastic as well. Both of those from lower than average solar cycles. And we do talk a lot about, as everyone, I know you have now because she mentioned it last time, but the Carrington event has dominated this issue in recent history. And the reality is I almost fear, from my perspective, that it's dominated it too much, and we've given people almost a false sense that this happened 150 years ago. It could happen again, but nothing really significant has happened between then and now. And I know that's not the point you're making, Lika, but sometimes I hear that as this obsession with the Carrington event. And I've got one slide here. The good news is, if you can read that, your prescription for eyeglasses is current. If you can't, don't worry, it's blurry anyways. So this is a good read, and I provide the link there for reference. Also great if you can't fall asleep tonight and want some leisure reading. But this is a documentation of all of the great impacts. and some pretty significant impacts. And the top date, I can see it more clearly here in front of me, is 1847. And a list through the late 1800s and 1900s of big impacts from big space weather events. So a quick read of this paper reinforces the point that a lot has happened, and space weather's happened pretty frequently. I think if we don't write these down and we don't go back and take a fresh review of literature often, I think we tend to forget this stuff. So space weather happens fairly often. So these are the geomagnetic storms, which I will elaborate on here shortly. On the left, the axis is 100 periods of storming, and these are months within a solar cycle. So the top panel starts in 1934, late 33, and that's solar cycle 17, not that unlike the one we're in today. And you can see these storms happen throughout the solar cycle. So I have an arrow here in each of these panels denoting solar maximum, and another arrow to the right in each panel denoting the solar minimum. And you can see that for geomagnetic storms, there's no strong preference of when they happen in a solar cycle. You can't really, with your eye, pick out the solar cycle trend very well there. So that's the level 5 storms. That's kind of on the lowest of what I'll describe. Here's jumping kind of mid-tier to kind of a category 3 storm for us. You can see the axis over here has dropped to 40. They become much less frequent, of course, but they've happened a lot. So when we get a G3 storm, which is what this is, and we get questions of what will happen, will technologies be affected, I like to point back to this to say they happen a lot, and that society has survived many, many of these. So part of my job is to coach so we don't have an overreaction. What is very, very clear in this bottom solar cycle, this was updated a while ago, but the point is the same, is that we've had very, very few periods of strong storming this solar cycle. So compared to last solar cycle, we're way behind in expected number of storms where we thought we would be or could be. And here's what really matters. So these are the big storms. These are our category 5s. There are some limitations to this. In our business, not all category 5s are the same. Some of these are much bigger than others, potentially by a factor of 5 or 10 even. But these are the big storms. So as I argued earlier, to look back for the last truly significant period of space weather, here's that bar showing up in late 2003 from that October, that Halloween storms as we call it. Then you have to go back to July of 2000 and March of 89 before that to see truly big space weather with widespread serious impacts globally. And with this March of 1999 storm, it drove collapse of the power grid in Quebec, leaving 6 million people without power for about 9 hours. And I will most certainly come back and elaborate quite a bit on the power grid risk. That was a big wake-up call to the industry, and certainly Hydro-Quebec and the owners and operators of those systems have learned a lot. And I think what you'll see later on is it's taking that knowledge, taking those lessons learned, and applying them across all of the power grids so that as a whole, the grid is ready. So we're making progress on that. So I want to talk through a little bit of our forecast sequence of events now. So as I said, this is an active sun. Those large and complex sunspot groups have the potential to produce very, very significant activity. Now, exactly the minute before that flare starts, I can't tell you that it's going to happen. It's just kind of that eruptive nature of the business, and I have very, very little insight into the specifics pre-eruption. And as I said, that first indication is that flash of light or radio waves, and we measure it. This is a 3-day plot here. It's also logarithmic, so you can see orders of magnitude increase in tens of minutes timescales. So that's our first indication that there's been a large eruption on the sun. We start watching for an increase in the radiation near Earth, and you'll see a great example of that in a movie here in a moment. And then the last piece is watching for whether or not part of the sun's outer atmosphere was explosively blown into space. So we talked a lot about eclipses. These are very, very important to us in the observational part of our business. And that white circle behind these in these coronagraph images is really the outline of the sun. So the red from the ESA NASA SOHO spacecraft shows a close-in view. And then the blue, which you'll have to wait for, evidently, shows a little bit wider perspective. But this red one is a nice one. So this is from the Earth's perspective. So that's one going away from us. You'll see an example in a moment of one coming straight at us that looks more like a halo. So we'll walk through this a couple times. You see the flash. We'll zoom out a bit. You start to see snow on these detectors. Those are the radiation. Those are those protons passing through and depositing energy in those imagers. And it's so intense, essentially, that it snows out these imagers. And if you have a satellite that's maintaining orientation by tracking the star field, which is very, very common, they can have orientation problems during these events as one consequence. Watch that one more time. And so this is at this phase, I say something significant has happened. We get a guess at how fast this is going. We know it's headed straight at Earth, given the shape and correlation with an eruption on the front side. But at that point, it's pretty tough for me to say, like in that case, was that a once in 10-year eruption? Is that a repeat of the Carrington event? Is it a once in 500-year eruption? At that point, I really can't say because they all look about the same. I would argue if you had a movie for the Carrington event, it wouldn't be that much different than that. And those CMEs associated with this event made their way from Sun to Earth in about 18 or 20 hours. And the Carrington event had a transit time of 17 hours and 40 minutes. Yes?
Refresh us on the Carrington event, what, when, and why. That was a bigger event.
Yeah, so the question was a refresher on the Carrington event. And so it was in 1859, and amateur astronomer Richard Carrington was making a daily sunspot drawing. And he was drawing a fairly large, complex sunspot group, and he saw bright white lightning on the paper as he drew it. So there was a pretty intense brightening for about 5 minutes. That was the solar flare associated with the event. And then about 17 hours, so we had that time. About 17 hours and 40 minutes later, we saw commencement of a geomagnetic storm globally. So deviations in magnetometers, compass needles, and pretty much worldwide visibility of the aurora. So reports of people in Cuba reading morning newspapers by the aurora, for example, campers in the Rocky Mountains being awoken, thinking it was dawn already. So a pretty fantastic example of truly significant global geomagnetic storm. And on that point, as you look back through mariner records or ancient texts, you can find lots of accounts of essentially globally visible aurora. So the sun is something like 4.5 billion years old, and as Lika said, it's been doing what it does for a long time. And so lots of accounts of this happening over history. Yes?
So I know you can, Doug Kammerer from WRC in Washington. I know you can look at that and you can see the sunspots. You can say, okay, conditions are right for CMEs.
Right.
What kind of lead time do you have, or do you not have any until you actually get that flare going?
Right. So I think at this point we're able to say that it's possible, but it's hard to go too far down the path of predicting anything with respect to a specific storm until we get that eruption. And you'll see that in my next slide. So once we see that eruption, we get an estimate, and I'll go ahead and jump ahead to that. So we have the model the little bit different view of the model you saw earlier, but we'll get a sense of what direction that's headed, how fast is it going. And that helps us to refine arrival time, and whether it's going to be a direct hit or, was there a big radiation storm associated with it, or how big was the flare. My forecasters use all of those as fairly loose correlations to take an educated guess at intensity at that point. So as soon as we see that CME, get enough time to model it, visualize it, put it in our models, then we'll make a prediction of onset and intensity. But until we get that eruption, we don't have enough information to go down that path with any certainty.
Very similar to an earthquake.
Yeah.
Where you know the conditions are correct.
Yeah, so the comment was very similar to an earthquake. I get a hard time. I have a good friend who's a pilot. He always wants to know what the aurora is going to be for his flight, like tomorrow or the day after. And I have coached him over the years, don't think of me like weather. Don't think of me having that kind of predictability. He lives in the volcanic ash community as well. I said, think of it more as eruption. So I may be able to tell you there are some pre-eruptive signs of volcanic activity, but until you get that eruption and start to characterize that, from a volcanic ash perspective from aviation, how high is the ash, where's the plume going, it's tough for me to say much. Lika, comment from you.
No, I was going to make another point on the Carrington event. So the internet of the Victorian age was the telegraph lines, and they were set on fire. Wow. That's kind
Right.
of the other side of it. Yes, absolutely, literally. And the point about your question, we really don't have sort of the physics insight, So the the photosphere is sort of in a state of either flaring or not flaring. That's kind of how we approach it right now. as Bob is saying.
Yeah. So I think the other thing too, as I said, important for me to remember is, and this makes it tough when you talk to critical infrastructure customers, because I see that big eruption like the one I just showed you, and I have to say that essentially at this point, hey, something big is possible. And that's really, we're honest about the state of our abilities at that point, because that gives them the heads up that they need to say, hey, something tomorrow is possible. But really we have to get into measuring what's in that CME before we get to make any estimates of the intensity. So we put that in the model, get to run it, get an arrival time, and then we really sit and wait with no new information until it makes it to the Discover satellite, or formerly the ACE satellite, that sits on the Sun-Earth line. So it's only 1 million miles upstream of Earth. So that CME, or that cloud, is made at 92 of the 93 million miles from Sun to Earth. And then as it passes over that in situ monitor, 1 million miles upstream, we get information about what's in that cloud. So that's what's depicted in this middle panel, lots of colored traces there. The yellow one is the velocity, and these are numbers that are hard to put our minds around, but it jumps from something like 400 kilometers a second up to 700, 800, 1,000 even. So we get a big discontinuity, and then we see an increase. This is the other, oops, didn't mean to do that. Other important set of lines, one of the other important sets of lines, is the magnetic field strength. So you have to bear with me, I've got a mic in one hand. But if you think about bar magnets, and you think about putting opposite ends, so say this is positive and my thumb is positive, these magnets will snap back together pretty strongly. And so when the orientation of the magnetic field within that cloud is such that it's aligned opposite to Earth, we get very, very strong coupling. When you, just like taking two bar magnets, you put the like ends near each other, those are happy to kind of repel or push off, and you don't get as strong a coupling. So until we can see whether the magnet is like this, and really how strong that magnet is, we don't get a lot of certainty on how strong that storm will be. And I'll give you two examples of where the correlation with velocity doesn't help a lot. One is in the August of 1972, so no one remembers the great Aurora or black. It was a big storm, but there was no big blackout. There was not. We don't talk about that one today from a geomagnetic storm perspective. It was actually the fastest CME we have on record, and again, acknowledging we've been paying close attention to a 4.5 billion-year-old star for a very finite period of time. But the magnetic field orientation, for the strongest part, for most of it, was oriented, as I said, to where it was in the same direction as Earth's magnetic field. So we didn't get a really, really strong storm. So should that have been opposite, just by chance, equally likely that it could have been, we'd be talking about that storm as one example. That March of '89 storm that I talked about, that transit time was about 55 hours. So that would have been a case where we would have seen a pretty big eruption, would have made predictions for some storming, but we would have been caught essentially with no notice, and we'd be playing catch up once we realized the true intensity of storming. Yes, Lika? As long as what you say agrees with me, please hand her the mic.
No, it's actually a question. So of course, magnetic field is critical for connection, but wouldn't you say that the punch also is very significant? Because if we sort of distort the magnetosphere, that itself will generate a lot of fluctuation.
Absolutely, very true. So I'm giving you the story to first order. Of course, there are a number of details beyond that. So the density is also shown on there. So really, if you think of that cloud, how dense it is, how fast it's moving, some of the very, very extreme deviations in the magnetic fields it induces on the ground, which is important, can be very, very strong at storm onset. So that's also an important part of storming. Generally, we see the main phase of the storm, or the prolonged period of the storm, after onset and deep in that storm phase. But yes, a lot of what I will say today is only true to first order. So, but thank you, very good point.
A question for you on CMEs.
Yes.
So what is the range of speed on them, and what would the average be? And you know, if they're going to produce an aurora, is there a correlation there as to when we would see it?
Yeah, so the timing helps to know when the aurora will start. What we don't get, as I said, is really the intensity of the aurora. So I would say that most CMEs are average, between 48 hours, maybe a little more than that. So on the fastest end are those 14, 15-hour storms, which are truly exceptional. 18, 20-hour storms are pretty exceptional as well. Anything that generally drives significant storming is, gets here before 36 hours, but I just pointed out a good example to the contrary. But we can have CMEs that leave the sun and are very, very slow and essentially transit at that same speed as that ambient solar wind. So we'll see the signature show up. We see no shock because it's not moving faster than the medium that it's in, but we'll see the magnetic field signature show up 4 days later. So it's kind of, we generalize on that 1 to 4 days, but the important part is on that before 1 day level. So and then essentially we get better information. This will come out as I talk more through this. But then we observe what's happening on the ground. So the panel on the right is the ground-based magnetic observatory, and I'll tell you why that's important as we go. These are the NOAA Space Weather Scales. So they go category 1 through 5. They are a great tool for communicating. They are a double-edged sword, though, because it's tough to generalize. Not every G3 storm, for example, has the same impact on GPS. You know, sometimes you can see strong impacts at a G3, sometimes you see none. So there are limitations to this, but we categorize each of those phenomena I talked about on those levels that help us communicate at least initial information, and then a lot of times we have to supply supplementary information where we have it through graphical products or short-term forecast products. The other thing, too, that's a bit misleading, these were designed with the Saffir-Simpson or Fujita scales in mind. There isn't a Category 1 hurricane that makes landfall. It doesn't have an impact. However, there are Category 1 space weather storms that happen all the time that no one notices. At least most people don't notice. I mean, maybe if you're using sensitive technologies, you do. But there are a lot of level 1, level 2, level 3 storms even with no significant impact. So we talked a bit about the July 2012 event. I will give you my perspective. So I have to brief FEMA on the first Wednesday of every month just to keep the communication lines open at the national level. And that's really, in the case we do have this big event that may have impacts on critical infrastructure, they're hearing about it with as much lead time as possible. That's what the sun looked like on July 11th. July 4th was a holiday. It was a Wednesday. So I got to brief this on the 11th, and essentially all I could tell them right then was significant activity is possible. And that's the truth. And so this region made its way mostly across the visible disk or facing Earth and produced kind of mid-level activity on the scales. And as Leek already pointed out, it got a few days behind the limb on the right there and produced one of what I would argue is probably the 3 fantastic eruptions of the solar cycle. So even though this solar cycle has been very small, very suppressed, we have had significant activity. Earth just hasn't been in the way. And even as recently, so we've had very few sunspots recently, over the last year and a half. And in September, we had a fantastic, very, very fast eruption headed away from Earth, kind of straight to the right, essentially in this graphic. But there is no spacecraft out there to measure the magnetic field strength and orientation of what's in that cloud. So we have no way to speculate or model or analyze the could-have-beens associated with that event. But Earth has been fortunate that it hasn't been in the way. So this is a close-up of that same storm. So I just described it pretty perfectly. Here's a big eruption. I tell you it's going to happen. Then I give you better information when it gets close. Sounds great, right? Well, I don't always get it right. And so this is a forecast we made. If you look at this, the beginning of March 17th, and we've issued this 30 minutes after midnight. And because we have global products, we work all in universal time. But essentially, we said not much is going to happen. We said those red bars are going to get to that 5 level on day 2. And guess what? Within 9-10 hours, we were sitting at a level 8 or a G4 storm. And what happened here almost is kind of the worst case for us. So when we get that big eruption headed right at us, that's pretty easy for me to say it will impact Earth. This one was one that we thought was going to miss, and because we're working from a very limited set of observations, just projecting a 3D object into one plane of sky projection, we got it wrong. And this did affect Earth, and it did affect Earth fairly strongly. So it doesn't always work as I've described. Yes? I will say that 60% of the time we're right every time. It's the other 40%.
Kind of wanted to make a point, sort of the science understanding we are gaining. So this July 2012 storm that we are talking of, the reason it was so fast, if it didn't have the stereo perspective, we would not have known. It was sort of what we call cannibal CMEs, one after another, really sort of creating a vacuum in space and pushing it through. You know, otherwise CMEs kind of travel in the ambient velocity of solar wind. So there are lots of things we still don't know. And these new perspective and observations are actually teaching us those things.
Right, yeah, a lot to be done in the science, for sure, that's a good point. So when we talk about event-driven product definitions, this is by no means the sexiest slide I have, but I'll tell you what products we have for these different phenomena. As I said, like the flares are no-notice events, so we're really just telling you when it's happening. We can't give you a short-term warning, or we can't put out really a watch. We'll do a probabilistic forecast. We don't really do a watch product for the next day. So watches are the longer lead time, lower confidence. Warnings are short-term, very, very likely to happen. We try to keep this to where we verify most of those. And then alerts in our business are essentially we've observed the conditions exceeding whatever threshold we've set. But you'll see that sprinkled throughout the next few slides. So for solar flares, and I described this quite a bit already, so as soon as it's being measured at the GOES spacecraft in geosynchronous orbit, it's already affecting the day side of the Earth. These last from minutes to hours, exclusively a day side effect, as I said, and because we don't know when that eruption is going to happen, we only have those probabilistic forecasts. When we do exceed that level 2 on our storm scale, we send out an alert immediately, and it links to this graphical product that I'll use to assess the impacts to HF. And this is really, it affects the lowest frequencies first. So sometimes you can mitigate this by going to higher frequencies, and I'll show you some examples of why that's important. But really, the situational awareness product, it goes with this, and then we send a summary post-event to say how big was it, because that can start to give people some information about, was this a really big event, and are we going to be looking for a geomagnetic storm in association with it? So this was mentioned as well, but sometimes the sun, when it erupts, can produce radio noise. This is a case, pretty exceptional, was mentioned already, about how the sun produced noise that looked like a GPS receiver. There are other examples of this, although they're not very frequent, and it can affect surveillance radars. There was an incident in Sweden a couple years ago where the radar was very low on the horizon. It was looking at the sun when a flare occurred, and it produced enough noise to essentially shut down Swedish airspace for an hour or two, which is problematic, of course. But this was a pretty big impact and kind of a wake-up to the GPS community of what's possible to GPS. So those green dots in the top panel, the numbers here, this is panel 1. The numbers may be hard to see. Panel 1, 2, 3. And then the dots on the timeline are here, superimposed 1, 2, and 3. 3 is at the peak of intensity. That total span is just about 10 minutes. But you can see in the top panel, green dots, normal operation of this pretty sophisticated GPS network worldwide. It's a good reception of signals. This solar flare starts to produce this radio noise that's the same frequency and polarization as a GPS signal, swamps the GPS signal. And so for a period of 10 minutes, GPS on the southern side of the Earth wasn't reliable. So if you're driving here this morning, didn't know where you're going, is that a big deal? Probably not. You've got enough visual cues. You know, you don't suddenly jerk the wheel to the right because your GPS told you to. However, if you're landing an aircraft in very, very low visibility conditions and this GPS outage happens at the wrong time, that's a very bad day. So big wake up that secondary navigation systems or even monitoring of systems that use GNSS for safety of life navigation is critical. So this is going back a little bit to different phenomena. This is the HF impact. So over remote areas, and it showed up in the video, my colleague Bob Maxson from the Aviation Weather Center said, if you're out over remote areas where there are no line of sight communications with the ground or air traffic control radar, you're reporting positions either by HF, usually in a tertiary mechanism, or sometimes in satellite communication. But HF is still pretty widely used worldwide, and so this is an example from March of 2012 where there was an uncertainty about an aircraft, a safety aircraft, traveling from Vancouver to Tokyo. So it was over 30 minutes late in reporting its position and checking in. And it's important to know whether you have an aircraft in distress, whether you need to dispatch search and rescue, whether you have a situation on an aircraft. But so that's why this situational impact graphic is up in those communication centers, so they can look at that. And even though we couldn't tell them exactly at this time tomorrow that was going to happen, they can look up at that graphic and see that the sun and the changes to the environment are likely why they can't use HF to reach that aircraft. Yes, sir.
Hey, Howard Bernstein, WSA in Washington. Recently there were some satellites launched that were supposed to enable real-time tracking. We remember with the Malaysian air flight that disappeared. If there's a solar flare, will that still impact, if you're familiar with that newer system going in, will that still wreak havoc on that system?
Yeah, so the ACARs and the automatic aircraft reporting systems, and I'm not authoritative, but I know enough to I think, answer your question. In general, no. Satellite communication impacts and sporadic satellite communication problems are possible, but generally those are fairly short-lived, with rare exception. And a lot of those satellite constellations use multiple satellites, to where even if the signal to one satellite was disrupted, that it could make communication or could make contact with another satellite. So I think those in general, satellite communications and satellite position reporting for aircraft, are pretty robust. Little bit of disagreement out there on that, but I think that's true. Yeah. Yeah, well, I think time has told. If there were lots of impacts, we'd know about that. So I think they're pretty scarce, but there's some people still holding on to that pretty firmly. So on, and it also brings up really a good point in that the changing role of HF and the changing role in all of these technologies. And so HF use is still very, very prevalent in the aviation industry. But I think I saw a presentation from the people who run the HF communication networks for aviation. Used to be AirRink, and I think they've been acquired by Rockwell Collins. They presented at a polar aviation meeting I was at this last summer, and they said every aircraft they had going on a polar flight had was equipped with satellite communications. So the role of HF is changing, but in September there was a aircraft coming from South America to North America, and this is from my colleagues in the French air traffic control authorities, and they lost track of that aircraft in September of this year for 90 minutes, which is a big deal if you don't know where an aircraft is for 90 minutes. And that was because that aircraft was not equipped with satellite communications. So they had no real way to reach that on backup channels. So it still happens. The aviation industry is changing, but it's still possible, and this impact won't go away anytime soon. Any other questions on that before I?
All airlines that are doing polar flights are doing SATCOMs?
Yeah, I think all of those, multiple carriers in that. The trick is, and I'll show you when we get to the radiation piece, is that there are two satellite constellations in use, Inmarsat and Iridium. Inmarsat is a geosynchronous-based constellation, so because of the curvature of the Earth, above 82 degrees, you can't use it, so you have to use HF. So like if you had Santa Claus is not getting DirecTV, the dish will be pointed at the horizon. So that's the crux of the issue there. However, Iridium's market share, I think, is growing, and there are Iridium-equipped aircraft as well. So it's still an issue out there, and HF is still big in polar ops. What that looks like in 10 years, I could guess, but hard to say. And I will come back to that. And I'll come back to it right now. So the radiation piece is really the next piece, and this is a 3-day plot again. But unlike that solar flare phenomena where you see it subside in tens of minutes, these levels can really persist and even continue to increase for days. And so that's what you see there are two eruptions. So you see a big enhancement, it starts to subside, and then you see another enhancement that pushes those levels back up. And that's pretty typical for very active solar region to produce multiple events. And it keeps it confusing, it keeps it busy, as I said, for a week or more during some of these historically busy periods. So it affects astronauts, satellites, and space again. And then for a little different reason, but essentially shown reasonably well in this patch, it can black out high-frequency communications again in the polar region. So these are just a sprinkling of the polar routes that are used, but as I said, above 82 degrees, a lot of reliance on HF. So this will really, really affect high-frequency communication for days when we get big radiation storms. So a lot of the airlines today will mitigate by flying below that 82-degree circle so they can maintain satellite communication, but that doesn't solve an issue that was raised earlier, and I actually added 4 slides at the break to talk a little bit more about the aviation radiation issue because there was a few questions on it earlier, but it doesn't really solve. You can see that radiation issue goes down to 60 degrees, and it's pretty uniform from 60 degrees to the pole. So when you get big events, you can get increases in radiation around the pole. So you're not really, by solving the communication issue, you're not really solving the radiation issue, and there's growing awareness of that, but I'll dig into that a little bit more in the next few slides. Any question on that before I jump into that? So, pardon the white space, I pulled this from a different formatted presentation. These are the top panel. It's a bit technical, but I wanted to get into it based on the question earlier. So these are background radiation rates. These are GCR driven, as Lika described. That's that constant term, that if the solar cycle is very suppressed, that will rise. And this is the dominant issue for career exposures for pilots, passengers, and crew. And there is a growing awareness of that. So you can see this is a flight from Munich to Chicago. And you can see it's pretty steady, right, at that 4 to 5. Don't worry about the units, microsieverts per hour. The 4 to 5 units, and then here's that big, these are the radiation levels in the second panel. That's the Halloween storms from a radiation perspective. So it takes takes radiation of very, very high energies to really, truly influence exposure to aircraft altitude. And to get significant increases is pretty rare. Over a decade, you're probably talking 10 or 20 hours in reality when you've really exceeded a factor of 5 or 10 above those background rates. It's not very often. However, it's very important to know when you're having those 5 or 10 hours of elevated exposure so that you can make the right decisions and reduce people's exposure. So I'll zoom in on this a little bit. So these are the flights during the period. So this is normal background conditions. You can see you get a couple flights that are pretty elevated above background. But note this is a linear scale. This is 30%. This isn't 300%, 3,000%. And then actually after the event, you get some benefit from that eruption working against that background radiation term. So if you add all of these up, you might have actually reduced your total exposure from staying on this Munich to Chicago flight through that entire radiation event. Now, I'm not arguing that you caught necessarily the very, very peak of the exposure there, but I think it needs to be taken into perspective. And that's really the point of my next slide. It's a bit thought-provoking, but bear with me. I should also say I'm not a health physicist. I'm not a doctor. Those people should help people make informed decisions about radiation exposure. I worked in the NASA Astronaut Radiation Protection Program for quite a while. I understand those paradigms, so don't get this official advice from me. But I think it is a responsibility of the space weather community and the aviation community to put that type of information in people's hands so they can make informed risk-based decisions. So this is about exposure. Quick show of hands if anyone wants to ingest any of this. For those of you who have seen me give this before, don't give it away. So known lethality of 192 milligrams per kilogram in rats, estimated of up to 200 per kilogram in humans. Does anyone want to give some a try? It's caffeine, right? So we've all probably had some today. And it goes back to, I think, what the father of toxicology, Parcellus, said, only the dose makes the poison. That falls a little bit apart with radiation. There's an assumption generally that any exposure comes with an increased exposure and risk. So it's not a perfect paradigm, but it does really raise the point that, like, I fly all the time, and it's not the biggest risk factor in my life. I have a friend who had a long career flying polar operations. It's not negligible for him, and we've discussed this, but if you're flying a lot for a career, you may get an additional %, maybe more, of dying from a fatal cancer. But you have to keep in mind that's above the background average of about a 30% risk of dying from cancer. So we're still working on this problem. I think really the point I want to make is that when we say radiation, there's a huge reaction to avoid it at all cost, even without really understanding that. So within that same September event, worst case scenario, if you would have flown at the exact wrong time over the pole, you might have doubled that daily background exposure. So throwing air traffic management into chaos, having airplanes descending and adding risk of collisions and things like that is probably not, you have to make that risk trade, I guess I would say. But we see an overreaction. Lika, you have a comment?
Sorry. So this radiation issue is, so I would say that we want to know it from knowledge perspective. As we move forward, our technologies are becoming more sensitive. We are making airplanes that's from being mechanically operated is all software driven. There's just so many issues. We are not thinking of future, how this can actually affect us. So I would say that we want the knowledge base. We want to kind of understand the environment and let it take the direction wherever it takes. And there's one other point I wanted to make, and that is, I think what we are kind of finding out from recent astronaut studies, it's not cancer risk for radiation, dementia. We are learning new things.
Right. Yeah, absolutely. Very, very fair point. And I don't want to lose too many of you and go too far into this, but a lot of what we know about human radiation exposure is from accidents or the Hiroshima and Nagasaki survivors, which are a different kind of radiation than you get from high energy radiation in space, what's impinging at the top of the atmosphere. So yes, certainly we don't know enough about radiation, so there are uncertainties included in that, and that's why it's very important for the medical community to kind of get a consensus of what is the appropriate exposure, what are the limits, and there are reports out there that pilots are, in fact, the highest occupationally exposed radiation workers population. So these issues are getting a lot of attention. They are very complicated, and I guess the point that I want to make is I see an overreaction sometime when there is no real risk. It's more of a perceived risk, and I think it's the responsibility of the space weather and the health physics community to get it to the point that someone's not afraid to step on an airplane because of this without truly putting it in perspective. I had a banana this morning. Bananas contain a radioactive isotope of potassium, but I think the health benefit of ingesting that banana was probably outweighed the extra exposure that I got from that. But exposure's everywhere, and it's just keeping that in perspective, because radiation is a very sensitive issue, and in the absence of true information and being able to convey risk, people react emotionally to it. Yes, sir.
Joe Murgo from WTAJ in Altoona. So you mentioned it. Are there any studies? Did anyone do a study on whether there is an elevated cancer rate among pilots? I mean, we've had commercial aviation for decades.
Right. Yeah, that's a great question. So NIH, National Institute of Health, has some studies, and I've seen them present. And essentially, it's inconclusive. And I'll try not to use too many words with more than 5, 6, 8 syllables. But so there are lots of confounders in these studies. So if you look at a pilot population, that's NIH study. I don't say this to be derogatory in any way, shape, or form, but I think there were things that showed up, like in flight crews as well, higher rates of suicide, alcohol abuse. I mean, don't take my word for it, read the study, but there were other things that showed up, and there are lifestyle things that may affect that incidence of cancer. So is it the sleep cycle disruption? There's so many confounders in that if it's just a small signal, let's say there's 0.25% above that background 30%, it's tough to pick that out. But it is being studied. People are watching it. If it was a huge signal, we'd know it for sure, but it's on that order. And the same for most of the astronauts is if it's a small enough signal, it's tough to pick it out. But that's the importance of the astronaut longitudinal health study and watching for incidents of cataracts, for example, and all of that. Yes. And I'm going to have to give up on radiation stuff. We've pushed the limit of my knowledge.
Yes. No, I'm still kind of trying to sort of understand. I think you are absolutely right. We shouldn't be kind of raising the risk factor when we don't know what risk means. But by the same token, I want to know what exposure I got, and we are not getting that information.
Right.
And that, to me, poses a problem. We just don't understand our environment, even as we are trying to kind of get out of low Earth orbit.
Yeah. I've got great news for you, and that's that within the international aviation community, and I work with that organization, within November of 2018 is supposed to be a commencement of global aviation services that is supposed to tell everyone when this happens. And there will be, just like icing or turbulence, there will be 2 thresholds set, moderate and severe, that have some derivation in radiation health risk and literature, for global awareness of, in these geographic areas above these flight altitudes, you have exceeded either the moderate threshold for radiation exposure or the severe. And I think when you start to get that type of information out there, you start to put the information in the hands of pilots, air traffic control, to make informed risk-based decisions about how to minimize exposure. And I think in that September event that I mentioned, I saw some text from an email from a colleague who will remain unnamed that said it's a fantastic radiation event, huge. There's inevitably substantial increases to radiation exposure over the continental United States. And I heard reports of aircraft requesting to change altitudes in the Caribbean. So completely inappropriate. And that happened because we don't have the right information out there at this time. So we're trying to solve that. But I catch me at the break if we want to go beyond that. I got 35 minutes to say everything else I want to say. Less than that, I'm sure. So the geomagnetic storm piece, I'll go quickly. I've described how this phenomena plays out. We've talked about these average arrivals. I want to show you what happens to performance of GPS systems. So this is the FAA's Wide Area Augmentation System. This is, again, that same 2003 example. Sorry for the resolution there, but you'll get the point. So they can take ground-based corrections and transmit those to aircraft and correct it so that it's within the vertical, good enough for the dynamic phases of flight. So during a 15 and 11-hour period during that Halloween storm, that red is in excess of 70 meters of error in the vertical, and I believe this system shuts itself off completely at 50. So you lost GPS-based approaches for a day in October 2003. So it's possible. And the other thing that gets tricky is if you're taking off from Frankfurt, landing in Rio, you expect bad weather, you want to use a GPS-based approach to get you in. Knowing that tomorrow this might happen is a lot of added value because it may influence your decision in putting on more fuel to get to a second alternate airport if you don't think you can use your GPS-based approach on that one. So just a simplistic description of what's happening here, and probably happened this morning at the pool over at the Marriott. So if it's completely still and clear, and I would have set a quarter at the bottom of that pool, you'd be able to see it's round, it wouldn't move. You may be even able to tell if it's a quarter if the water's clear and perfectly still. Let's say I cut my two kids loose at the other end of the pool and they try and drown each other. All of a sudden that surface becomes turbulent. Those waves make that quarter appear to move. So it'll appear to move in position. And there may even be brief periods of time where you lose sight of that quarter. So that's essentially what's happening. The signal's transmitted from space. It passes through the ionosphere and to the receiver on the aircraft or in the ground. And as that layer changes, that signal gets distorted, either adding increased position errors or loss of signal. So that's what's happening. Now, I'm an engineer by degree, a tech guy. I don't pretend that this is the story I can tell 10 years from now. And so aviation and their application of GPS is changing substantially. And dual frequency, so using more than one frequency allows you to subtract out some of those errors, the moving of that quarter. You can get rid of a lot of that. That's probably going to see more widespread use on the 2025 timeframe. And then multi-constellation, looking at more than one constellation, gives you more satellites in the sky. So you'll get rid of a lot of that error problem. But those brief periods when that quarter disappears, what we call scintillation, it's not a perfect solution for that. So these impacts to GPS and these impacts to aviation will change with time. So this is just an example. I'll spare you the details in the interest of time, but I've given you the extreme, but we see impacts at time, localized impacts for mid-level storms. So this was degradation of performance of WAS in Alaska during just a level 2 storm. So that kind of goes back to what I said about the NOAA scales. It's not, the activity and the impacts are not perfectly correlated with that storm intensity. So moving on to the risk to the power grid. That geomagnetic storm produces the aurora. That's a very, very strong current system. And underneath that aurora, it's the dominant driver of this, those changing currents induce changing magnetic fields at the surface of the Earth. And correspondingly, depending on the conductivity of the ground, down to tens of kilometers beneath you, induce electric fields, and that's really the most direct quantity that a long conductor on the surface of the Earth feels. And I want to emphasize long because I'm talking tens of kilometers, so it's not the cord plugged into the laptop there. We do get mixed up and even used interchangeably with electromagnetic pulse risk or EMP risk, and that's not the same. For the EMP people online or in the room, we look a little bit like the E3 pulse of the EMP, but we don't. Space weather doesn't present a risk to the smaller scale infrastructure. We're really talking exclusively about long pipelines or the transmission part of the system, the electric power grid. And in general, they define that in the NERC standards I'll show you as 200,000 volts and above. So it's not the lines running down the alley behind your house either. This is really a transmission side problem. So those currents end up in those lines and they end up on the transformers on both ends of that, and they can cause saturation, which causes it to create funny harmonics, which are not great for system operation, or there can be heating problems. A couple of examples shown here, pretty rare, pretty extreme, but you can damage the system, or the harmonics can cause it to be unstable and trip it offline. So this was a National Academies report that came out a few years ago from the National Research Council, and this was at the time, if the analysis I think was actually done against that 1921 storm, but if a 1921 or a Carrington event reoccurred, this proposed these were the probable areas of power collapse. And it also said that something like 400 of the major transformers, hard to replace, long lead time items, would be damaged, beyond repair, leading to prolonged response and recovery scenarios. So $1 to $2 trillion of damage, 4 to 10 years recovery. This is, I would argue, one end of that argument, and I think that certainly got a lot of people's attention. And after that, a lot of words here, but I didn't want to be misquoted. So even in 2012, NERC, which is the North American Electric Reliability Corporation, based out of Atlanta, quasi-independent industry representatives who have been granted from the federal regulatory side, not to overwhelm you with acronyms, but the FERC is the regulatory side on the federal side, and NERC is the industry side that has the responsibility to maintain the reliability and availability of the grid. And NERC came out and said loss of reactive power is the most likely outcome. So what does that mean to you? It means that they could lose system stability, you could have blackouts, but the difference in this scenario and this scenario is you don't, in this one, get widespread catastrophic transformer damage. You shed load, or you let the system fail before you ruin those transformers, which are really hard to build. Some manufacturing capacity has restarted on U.S. soil, but in general, if you have to replace a lot of them, it's a very, very challenging logistics problem. So there's some recognition that even if you don't end up in that long response recovery scenario, that a severe space weather storm or extreme space weather storm still represents a risk to the bulk power system. Yes.
Can you comment on, so we hear about the induced current issue. Can you talk about the importance of ground conductance?
Yeah,
because
absolutely.
I mean, these are all coupled phenomenon, right?
Yes, and I do have some slides where I'll show you that. And our knowledge is really maturing, and our understanding of this risk. I'll go through that, and catch me again once I do if there are more questions to that. You might as well leave that. Oh, I'm sorry, you're going to use it.
Yeah,
I'm just kidding.
When you talk about an event like, if you go back to that last slide, you're talking about the Carrington event, which you said is 150 years ago. Do we have data that goes back to show when another event like that occurred? I mean, I know, how far back can we go?
Yeah, not really is the short answer. And I'll use the biggest word I'm going to use today. So if you look at volcanic eruptions, for example, you could go pull a core sample 100 miles downwind, and you get some paleoclimatological record, right? It leaves a fingerprint and something we can explore. But for space weather, we don't really get that. So no, we don't know. And in fact, so for radiation storm intensity, they've tried to look at the radioactivation of moon rocks to estimate the frequency of very, very large solar particle events. But from a geomagnetic storm perspective, we have, as I mentioned, ancient accounts of global visibility of the aurora, which qualitatively is interesting, but it's tough to do anything quantitatively. And even with that Carrington event, really we don't have good measurements for that. So we've tried in some measures to estimate the intensity of that, and they vary by a factor of 2. I should also say that factor of 2 is not 20 times bigger than anything else we've observed. It's on that 2 to 4. So the Carrington event was not 100 times bigger than anything we've seen. But we don't know. But I'll show you some work on that using what we do have. So this is just really a copy of a ruling. It was on the regulatory side, the FERC side. They've put out a reliability standard for transmission system performance during what they call a geomagnetic disturbance. And so this is in version 1. Version 2 is being worked on to refine what we know. But in short, they will define a benchmark space weather event, which gets to the challenges you just talked about, and I'll show you the other challenges associated with that. And then industry, and I guess I should also note that the NERC footprint is all of the lower 48 and pretty much Canada. above us, so it's U.S.-Canadian effort, but it will cause them or drive them to analyze the system reliability against that benchmark space weather event and show that they can maintain stability. And if they have a certain transformer that looks like it's at risk of what's shown in the bottom panel there, overheating, to do a thermal analysis on that and even physically mitigate that where necessary. So we will be having, the grid risk is evolving, at least from a space weather perspective. Good engineers with time and money can design some of this out. Now, there's an argument, there's a trade space there about how many nines of reliability do you want versus how much are you willing to spend. So some risk will inevitably remain, but we will be engineering some of this risk out. I should also say, and this is the way FEMA approaches it from a power outage perspective, I don't want everyone in the emergency management community to take their foot off the gas on preparing for widespread power outage. Space weather is just one of the ways you could lose availability of the bulk power system. There are other threats such as physical attack, cyber attack, and those will continue to evolve. So there are other risks that will persist even if we do get a better handle on space weather. So this is I'll go quickly, I think I've described all this, but when we have a big event like the October 2003 event, you get global impacts across most all of these technological systems. So examples shown here with loss of satellites, for example, disruption to GPS-based drilling operations, aircraft disruptions. So when we get the big one, a lot of impacts system-wide globally. Any questions on that? Yes, sir. Well, the mic's over there, but microphone. I'm getting tired of holding it too.
Frank Billingsley from Houston. So this Carrington thing, and all the telegraph wires caught on fire. Those were made out of copper, and that's the largest amount of metal in your cell phone. So has it been considered that all of our cell phones could catch on fire?
Yeah, that's a great point, and that's what I was emphasizing. I'm sorry I wasn't super clear. I would love to. But so
I know, because I can go with that.
The key to the issue, and that was the point I made about the cord there. I'm totally fine. But the point was the length of the cord. So we're talking about induced voltages in peak intensity, like 8 or 20 volts over a kilometer. So that's I'm good. So that's just not intense enough. Sorry, my arm was feeling. That's just not intense enough to affect short conductors. So when we talk EMP, and not to go too far down that rabbit hole, we're talking tens of thousands of volts per meter. So that's when you talk, and the EMP reports are out there. So like a GPS unit, if it was unplugged, wasn't very susceptible, but as soon as you put a 1 meter cord on something, they saw susceptibility to that. So if you had in an EMP event, and again, this is a little bit out of my purview, but to answer your question, if you had a cell phone that was plugged in during a high altitude nuclear detonation of the US, might not be good for your cell phone. But right, there are other problems that come with that. But from space weather, because those voltages are so weak over those distances, it doesn't affect smaller scale electronics.
Any effect to gas lines?
So yes, actually it is. So gas lines, pipelines, and they're pretty clever at designing this, particularly the ones that sit under that aurora. And believe it or not, it's primarily a corrosion problem. So they will bias a pipeline to fight those currents from flowing because it can degrade the lifetime of those pipelines. So long conductors, tens of kilometers or more. Any other questions? All right, I'll try and finish about 10 minutes. Good? Yes.
I'm just going to throw it at you and you can answer whenever.
Microphone.
And the question is, again, I think we are making a lot of progress with the known. You know, are we actually keeping our eyes open for future technology that is coming up and how that would be sensitive to many of these threats?
Yes, and I mean, I could take this question from any angle. So aircraft avionics you mentioned earlier, yes, feature sizes and chips and things are becoming smaller. Aircraft have to design to standards to live with that background radiation environment, so I feel like that's fairly well addressed. The power grid, it's very important, and very strong emphasis on high reliability. So before any new system, in fact, devices to block this go in. There are directed and voluntary efforts to test these blocking devices, to fully understand. And if you look, that's NERC's position on that, is they don't want to rush into solutions. They want to fully understand, are the additional complexities we're introducing to these systems, do they really buy down risk? So in general, I'd say it's very, very calculated, and there's a lot of testing that goes into before anything new comes online. So what are we doing about this? We have the models that we showed you that view the eruption from the sun and get a better sense of when it will get here. And I'll show you 2 more examples, and I'll probably just go ahead and jump to the movies because it's a little easier to make the point. But once we get that solar wind data that I talked about from the ACE or Discover spacecraft, is we're getting pretty good at the physics of how we drive the Earth system. So we have a geospace model that will describe those changes in those magnetic fields. We have a model that will describe the changes into the satellite drag environment, for example, or that GPS impact that I talk about. Then essentially the electric field model that we can couple to that geospace model in a predictive sense to tell the power grid 10 or 15 minutes from now, these are the induced currents your lines will feel, so they can make decisions about how to safe those systems. So we are making progress, but it really is after we get that solar wind data. So if those CMEs are going very, very fast, you may be talking about 10 or 15 minutes really for that disturbance to pass from that buoy 1 million miles upstream of Earth to drive that system 10 or 15 minutes later. And I do so many of these, it runs together for me sometimes, but I don't think I gave the analogy, nor did you. But it'd be like having a hurricane making landfall in Miami, never getting a pressure or wind speed measurement until it comes over your buoy 50 miles off the shore of Miami. So that's really the nature of the business. But once we get that data 50 miles offshore, we can do a lot with it. So is it as good as doing it a day ahead of time? No, but we can't get there, and I'm not sure we will in the immediate future, so we're doing what we can. So a couple of examples of that. The other thing, too, is what we're trying to do is, on the left, classic text-based confusing products, which you all know and love. And that part was a joke, I know. And it's really tough for me, too. And I guess I'll make the point is, so if you tell me I don't know anything about weather, I'm the guy that you do the temperature icon for, the snowflake. I don't know. You show me a chart with isobars on it and wind vanes. I don't know anything. But I know what snow is because I walked through some. I know what it's like to be cold, and I know what it's like when the wind blows on me. So it's easy for me, even though I don't understand the underlying fundamentals of what you're doing to put that together, I can understand how that impacts me. Space weather, unfortunately, we get a lot of interest generated, and then these are all untangible with the exception of viewing the aurora. So radiation environment at aircraft altitudes, you can't see that. Changes in magnetic fields on the surface of the Earth, you can't see that either. So that's a big leap, and it's different things than people are used to dealing with. So we need to do a better job at it, but it is tough sometimes to go from this very strict text product that may mean a lot to an operator in the power grid to something that's meaningful in the general public. So we're trying, but it is challenging. But we are also, picture's worth 1,000 words, maybe 10,000 of words like that. We're trying to go to graphical nowcast or short-term forecast to give people better information and particularly capture the spatial and temporal variability. So this is where we're headed with providing a product for the power grid to say, what will their systems feel? So Lika brought this up earlier, and so I can understand the storm, I can understand the changes in the magnetic field, I can either observe them or predict them. But to truly understand what the induced electric fields on the surface will be, I have to know the conductivity of the Earth beneath me. And as I said earlier, it's down to tens of kilometers. It's really the lithosphere, it's the upper mantle and the crust. So it's deep, and it takes a survey. Now, the survey is a key word because you can measure it once, and then it doesn't really change on our timescales. But these are where the surveys have been completed. And this upper Midwest section should be completed this year as well. I think that's planned. But really, until we get this filled in, we can't really do thorough analysis of this power grid risk. So this is a big push in our community to fill this in. I'll show you a graphic in a minute of why this matters so much. Yes?
So, microphone.
Check one. Two microphones. Got one.
Two's better than one.
So where I live in Oregon, it's very red. So what is that saying that there's a lot of conductivity in the soil there?
Thankfully, those are indicative of the year or who did it. I'll show you that graphic in a moment. you'll get your answer. But that's an important question. That's the key, a really key question. And I think it's one after this. But this is, if we have that information, so this is where we have it, I think, on a 1/4 degree resolution. But our intent is, my intent is to make this work. This is a nowcast product, but I'll show you the model that we can use to drive it. So if we produce these induced electric field maps, a power grid operator can layer that in their system analysis tools, and then, as I said, make better decisions about what they need to do to protect their system. So this is where we're headed, is to go from that one text format of a global indicator into really specific spatial and temporal information. And that's what you need, and we've worked very, very hard in the last few years to get to this, really to support the power grid. So these are millivolts per kilometer. So when you look at extremes, I talked about this a little bit. So the NERC standard has something like an 8 volt per kilometer. So no, that's not a big number. This was not a big storm. This was just when we had it up and running. And then localized of up to 20 have been observed at times, which is a big deal. But these are pretty small numbers. So we've got to get this right and get all the color scaling right. And even a millivolt per kilometer isn't going to mean much to anybody, but this, if they can plug this into an analysis tool, is what they need. Yeah, I'm going to, yes.
Is there cross calibration of what you are predicting versus what somebody else at the other end is actually measuring?
Absolutely not. We just believe it as ground truth. No, yes, absolutely. And so what do they say? The only person who believes a model is the developer, and the only person who everyone believes in observation except the person that made it. Very important point is we are working very closely with industry partners to say, what did you observe and how well does this match to observed induced currents? And we are even trying to figure out how fine do we need to go on resolution, things of that nature, to see what really matters from that perspective. So all open work. These experimental's a very, very key word there. We're making progress, but still a lot of that work to be done. So I'm going to move quickly just so I don't run out of time. But this is essentially predicted magnetic fields. So this is one of those models that was in that chain that can predict the magnetic fields. Again, with as much lead time as you can get from how long that solar wind takes to propagate from ACE or Discover to Earth. And so if we can predict these, we can then do the predicted induced electric fields that I just showed you. The same is true, and in the interest of time, we'll neglect it, but we're big efforts for us to couple terrestrial weather models with our ionospheric models so that we can see the results of even big storms and convection on what that does to that signal, what that does to that layer that GPS signal has to go through from sun to Earth. And then hopefully the intent is for ultimately to understand the upper atmosphere and ionosphere is two-way coupling is what does that drive within the weather models. This is out of my domain, but it's my understanding that they have some improved skill when they go to couple the upper atmosphere and even predicting stratospheric warmings, for example. But we're trying, again, on that short-term predictive time scale. I'm almost there, Dave. So I've talked about this, and it's got national attention. So we have a Space Weather Action Plan and strategy. So that's comprehensive. It's FEMA, DHS, it's observations, it's science with our partners in NASA and NSF. So we've said, here's everything that's wrong. Let's try and solve it. That takes money. That's challenging sometimes. This is one of the things that it's doing is defining benchmark space weather events, and this gets to the question you asked. And this is essentially the peak intensity that this gentleman, he published this, he's authoritative in the field, thinks would be observed in a 100-year period at that point, not necessarily all at the same time. But you can see that on these small spatial scales that it varies a lot. So these black and red dots are big numbers. So those were years earlier. These are big numbers. So the upper Midwest has a high induction hazard, but the Pacific Northwest, at least according to this work, is in pretty good shape. And so what's important now that we have these survey results from the Northeast is to fill that in and find out where in the country do we really have the most risk. And that's what this Space Weather Action Plan is driving, so that knowledge can feed response and recovery plans as well. Corresponding executive order that got into some of the specifics, gave some more credibility to that action plan, and essentially this is one of the few executive orders that has persisted past the change in administration. So good support from a bipartisan perspective of continuing to look at the risk to critical infrastructure. We talked a little bit about, I already answered the question on GOES 16. So GOES are labeled here, but some continuity in that. What's important for us too is I've showed you these chronograph and in situ solar wind measurements. If we don't keep those, we are blind to what's coming at us. So the big thing for us right now is to maintain continuity in that. Why is that hard? So this is the Discover launch. It's hard because these are really expensive. So this is going to be the fastest burn up of $135 million you've ever seen. That's the launch vehicle alone. Total mission cost, $400 million. So even though we need these observations, we need as many as we can, the realities are we are observationally constrained because they're very, very expensive. So pretty amazing. And if you haven't seen a launch, highly suggest you take that opportunity. I'm not sure which I was more moved by. I was privileged to see a space shuttle launch, which was incredible. And then I got to experience the total solar eclipse. But both should be bucket list items without a doubt. There's no bucket list for space shuttle. I know. So I'm glad I checked that. But you're right. But any launch. So this is essentially a wrap-up that I have. And that's really information dissemination. As I acknowledge, we're trying to do a better job of communicating and making that a little clearer, particularly the general public. And I think the biggest interest is the aurora. I didn't put a slide in specifically on this, but this is our short-term forecast model. So if we predict a big storm tomorrow, and this is another one of those models that can kind of give you a tens of minutes prediction of whether or not you should be able to see the aurora. So if we do think we're going to get aurora tomorrow night, I always tell people, look at this before you actually climb out of bed. So that's prominent on the front page of our webpage. And again, we're trying to clean up the messaging and be more present on social media.
I have to ask a question on that.
Sure.
So what about
Dave, if I'm late, it's... This is my last slide. So,
what about the auroras that are like KP2, generated by substorm and others?
Yeah. So, I mean, there's auroras always present. You have to get good viewing conditions, which would be nice to pair with the, cloud layers and things like that. So big aurora. So the people that are used to seeing it at lower storm levels, like in upper Minnesota or Canada or Alaska, for example, they're pretty used to seeing it at mid storm levels. When it becomes, I think, more interesting to more people is when we get the bigger storm and you get the potential to see it where you usually don't. Or in the once-in-a-decade case where, like me living in Colorado, I'd have the opportunity to see it. So it's really the extreme. The people that get to see it often are pretty used to it. But that's a fair point. That's words of everything. If you don't remember everything I said, there it is. But in closing, I want to thank the organizers. I want to thank Dave again for the opportunity. I want to thank you all. I didn't see anyone leave, I don't think. So I want to thank you for paying attention to me. Yeah. So this is a beautiful venue in Breckenridge. I really appreciate the hospitality. I'm fortunate to live in Colorado as well. I promise you that is the view from my office chair. But I think the view from my hotel room this morning topped that. And I'm really, really happy to be here. Thank you.
That's awesome, Bob. Thank you very much. Unless you think that there's not as much interest in space weather, we've reached 21,000 people so far today with the live stream. So that's terrific. And I did just want to spend just a moment and remind everyone online that we're going to be reconvening back here in this room in Breckenridge tonight from 7 to 8:30 Mountain Time, so we can participate in a town hall meeting. We've opened the doors up to the town of Breckenridge to come in and hear about the 2017 hurricane season, which was so traumatic. It was just a really intense season. We're going to have folks from the Weather Channel. Paul Goodloe will be here, also from West Palm Beach, Miami, and Houston, Texas. So we had so many impacts there, and we're just going to open the doors up to Breckenridge. We're also going to have other scientists in the room in case the questions turn towards climate change or turn towards impacts or just the future of weather forecasting. So we hope that you join us here, and we thank you very much for joining us. I am going to ask anybody else in the room if you have any other questions for Bob, because we do have a couple more minutes. The stream will end at 12 o'clock, but I don't want to cut anybody off if you have any questions about space weather in general. And as you can see from Bob's great presentation, it really does impact all of our devices and our situational awareness. So, Jim, do you have a microphone over on that side, or am I holding it? Okay, here. Here you go.
At the, this is Jim Gandy from Columbia, South Carolina. At the AMS annual meeting, Dr. Sandy McDonald mentioned the need to really improve our infrastructure for energy distribution and telecommunications because of the threats that are imposed, obviously from nuclear devices, but more importantly from space weather that could impact at any time, really. That quite frankly, the distribution infrastructure is at risk, and we could do things to protect that. Any comments on that?
Yeah, no, and I had the pleasure of working with him for many years and co-located in the facility. His view was probably better than mine, actually. A little higher office, but yeah, so I think his proposal out there for a number of reasons is some reliance on a DC backbone within the grid, and I'd have to review all the details of the paper again. But he had some good points in there about how design choices will influence the future susceptibility of those systems. And like I said, a lot of very, very bright, I think the grid, very important, attracts the best and brightest, and they are looking at things like that. Even, for example, in the transformers that I showed you, designs of future transformers. There are some designs of transformers that are pretty much have a lower susceptibility to this phenomena. So as we've learned more about this, different design choices will be made in the future to buy down risk across many of these things. And often it is risk balancing exercises and cost balancing exercises. But I know DC infrastructure is certainly part of that conversation. And there are pieces of DC infrastructure. It doesn't solve the problem completely, but there are different impacts associated with it. But yeah, he's asking some thought-provoking questions and doing good work.
Well, great. Thank you very much.